So the question here says, Maya is an athlete who competes in 1,500-meter races. Last summer, her practice run times had mean 4.22 minutes. Over the winter, she has done some intense training to try to improve her times. A random sample of 10 of her practice run times, X minutes this summer, are summarized as follows. So sum of X is 42.05 and sum of squares of X is 176.83. Maya's new practice run times are normally distributed. She believes that on average her times have improved as a result of her training. Test at the 5% significance level whether Maya's belief is supported by the data. All right, so we want to perform a t-test here, seeing that we've got a small sample size. I'm going to start with the data that we've been given by finding the mean, the sample mean, which is sum of x over n. So that's like 42.05, and that's divided by 10, which gives us 4.205. Then I'm also going to find the unbiased estimate for the population variance, which we're going to find by 1 over 9 of 176.83 minus 42.05 squared over 10. All right, so for this calculation, I'm going to use my calculator here. All right, close bracket, and we get 0.001083 recurring. So 0.001083, the 3 is recurring. All right, so this is what we are having right here, and we're going to make use of this data now at some point when we perform the hypothesis test. The null hypothesis is the fact that her mean time is 4.22. The alternative hypothesis is that her mean times have improved. Okay. She believes that on average her times have improved as a result of her training. So if her average times have improved, or if her times on average have improved, it means that she probably runs faster, okay, takes less time to cover the 1,500-meter race. So mu should be less than 4.22. So that's what we have right here. So if the null hypothesis is true, we know that the distribution of the sample mean would therefore be mean mu, which is 4.22, and of s squared over n, which is 10 in this case. So basically this. So we can get the test statistic. And for the test statistic, we use t is equal to x bar minus mu. And that's over the square root of, okay, the square root of s squared over n. So this, therefore, is t equals to the sample mean. We got that to be 4.205. So 4.205, and that's going to be minus mu, which is 4.22, and that's over the square root of s squared. We got that to be this value here, 0.00108333, and that's over, okay, that's over n. N is 10. So basically this. So therefore T will come out as, now I do the calculation. This is giving us minus 1.44. All right, so minus 1.44 is what we're getting for the test statistic. All right, so next we need to find the critical value. And for the critical value, let us consider the fact that this distribution um, is a lower tail test, considering that this is less, mu is less than 4.22. So it's a lower tail test at 5% significance level. So I'm going to do everything in the lower tail. All right. So this critical T value, this is like the 5% significance level. So that's like the critical region right here, or the rejection region, 5%. All right. So um, we are going to find the test statistic T at 9 degrees of freedom. Remember, the sample size is 10, so the degrees of freedom will be 9, and the p-value will be 0.95. All right, so we will need now to use the tables for finding this value. So let me take you to the tables, and there we are. Okay, I'll scroll down to the normal part. Sorry, what do we call that? The T distribution, critical values for the T distribution curve. So 9 degrees of freedom and 0.95, 9 and 0.95. So we get that we have 1.833. All right, so we're going to work with 1.833. All right, so 1.833 is the critical value we're working with. All right, so if 1.33 is the critical value, therefore it means that here we'll be having minus 1.833. Okay, since it's in the negative, right? And minus 1.44 is actually greater than minus 1.8. That's where it lies. So we're saying here minus 1.44 is greater than minus 1.833. So it's not in the rejection region, but in the acceptance region, which means that we accept the null hypothesis. We accept H naught. So contextually, what does that mean? Remember, the claim was that the times have on have on average improved, right? So since we are accepting the null hypothesis, it means we are rejecting the alternative. We're rejecting that the times have improved. So we will conclude to say that there is no sufficient evidence to support Meyer's claim. So that's basically how we perform the test. That's how we do it.